Hi, we're Group B6. I'm Sean Dalesman here with Guy Lynn, and we're going to teach you about random variables, expectation, and variance today. The expected value, also called the expectation or mean, of random variable x on the sample space of set S is the sum of the probability of S times the value of S. When the sample space S has n elements, then the expected value is the sum of the probability xi times the value of xi. If x is a random variable, then the probability that the value equals some random variable r is the sum of the probability of the element S in the set of S. Then the expected value is the sum of the probabilities times the random variable r. The probability that the value equals the random r is the sum of the probabilities of the outcomes S such that the value of S equals r. The expected number of successes when n mutually independent Bernoulli trials are performed, where P is the probability of success on each trial, is n times P. And this is expectation with Bernoulli. An example with expectation. What is the expected value of the sum of the numbers that appear when a pair of fair dice is rolled? So we're going to begin by letting x equal the sum of numbers that appear when a pair of dice are rolled. The range of x is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. The probability that the value on the die equals 2 equals the probability that the value on the die equals 12, and that probability is 1/36. The probability that the value on the die equals 3 is the probability that the value on the die equals 11, and that's 1/18. Probability that the value on the die equals 4 is the same as the probability that the value of the die equals 10, and that probability is 1/12. Probability that the sum of the die equals 5 is the same as the probability that the sum of the die equals 9, and that probability is 1/9. Probability that the sum of the die equals 6 is the same as the probability that the sum of the die equals 8, and that's 5/36. Probability that the sum of the die equals 7 is 1/6. Therefore, the expected value of the sum of the die is 2 times 1/36 plus 3 times 1/18 plus 4 times 1/12 plus 5 times 1/9 plus 6 times 5/36 plus 7 times 1/6 plus 8 times 5/36 plus 9 times 1/9 plus 10 times 1/12 plus 11 times 1/18 plus 12 times 1/37. And what we did is we took the value of the die and multiplied it by the probability that that value would show up on the die, and then added them all together. And therefore, when you add them all together, the expected value on the die is 7.
Linearity of expectations. So the value of the sum of random variables is the sum of their expected values. If sum xi, I is 1 to n, with n being a positive integer, and if a and b are real numbers, then we have the expected value of the sum of the random variables is the sum of their expected values. And we also have the expected value of some scalar a times the random variable x plus another random b is equal to a times the expected value of x plus b. So here is a proof of the linearity. So here we're proving that expected value is the sum of the expected values. As you can see, this is the random variable x1 plus x2. So this equates to the sum of the probability of s times x1 of s plus x2 of s. And then we could split this sum into two sums, probability of s with x1, probability of s with x2. And then these two sums are just the expected value. So, thus this is true. Now for the second one, we have the expected value, and we turn this into a sum by definition. And then we could split this into two sums again. And here, we take b out in front and a out in front of the sums because they're just scalars. And then we can equate this to this here, because for this part of the sum, p of s is 1. And here, p of s and xs is not 1, not constant. So variance. So if we let x be a random variable on some sample space S, variance of x is the sum of the value of s minus its expected value squared times the probability. So this is related to the deviation of x of little s in the big sample space S, which is s minus the expected value. But because of the difference, it is sometimes negative, so we square it to get rid of the negative sign. If x is a random variable on a sample space S, then the variance is also equal to the expected value of x squared times the expected value of x, whole thing squared. And here's a proof. The variance of x is equal to the sum of this here times s. This is the deviation shown in the previous slide. So we equate that to this, which is just expanding the polynomial here. And then we can add all up the terms in the summations to get expected value of x squared minus 2 ex plus expected value of x squared, and which equals this. So we have a variance example where x of ij equals 2i. I is the number on the first die, and j is the number on the second die. So what is the variance when the two fair dice are rolled? So I has some value 1 through x, 6, and the probability has values of 2 through 12 because 2 times 1 is 2, 2 times 2 is 2, and etc. So the probability of x equals k is 1/6 for some k, 2, 4, 6, and so on, because you can't get an odd number when you're multiplying by 2. So the expected value of x is the sum of your values over 6, which is 7. That's basically the mean. And the expected value x squared is when you square all your values and you just divide by 6 again, just like the mean, and you get 182 over 3. So the variance of x is this here, which is 182 over 3 minus 7 squared, which is 49, and that's 35 over 3. Here we have another example. Suppose that we roll a pair of fair dice until the sum of the numbers on the dice is 7. So what is the expected number of times we roll the dice? So there are 6 possible ways to roll 7. 1, 6, 2, 5, 3, 4, 6, 1, 5, 2, 4, 3. So the probability that you roll 7 is 1/6. Based on the Bernoulli theorem, n is equal to 36 total outcomes, 36 possible ways to roll 2 dice, times its probability, which is 1/6. That's the success of getting a 7. So 36 times 1/6 is 6.